Neurons use electrical signals to coordinate thoughts and actions. The majority of ions found inside the neuron are anions, leading to a negative interior, and there is a greater density of cations outside of the neuron. These opposing charges across every cell membrane can be measured through the use of a microelectrode. This electrode has found the resting membrane potential to be roughly -50 to -80 thousandths of a volt, the negative polarity of the cell being represented through the negative measures of volts. Ion channels are pores that form from passive transport, allowing specific ions to cross the semipermeable membrane. Selective permeability means that some molecules travel freely while others are stopped. Two forces aid in transporting potassium ions across the membrane. Diffusion is when molecules of a substance travel from areas of high concentration to low concentration down their concentration gradient. The molecules that can cross the membrane this way will continue to do so until there are equivalent concentrations on both sides of the membrane, resulting in equilibrium. The sodium-potassium pump pumps 3 sodium ions out of the cell and 2 potassium ions into the cell. This will take place in the neurons, both ions continuously being sent in one direction, then traveling back down their gradient. Potassium moving down the gradient creates a net negative charge with the neuron, which then exerts electrostatic pressure, bringing the ions back inside. The Nernst equation predicts equilibrium potential. The Goldman equation takes into account the concentrations of potassium and sodium ions, both in the intracellular and extracellular fluids. This accounts for the degree of permeability. A threshold amount of depolarization triggers an action potential. Action potential there are significant changes in neuronal polarization in an extremely short period of time. It creates a pattern that translates into a code that holds the information destined for the target cell. There are two concepts that are important to the triggering of action potential: hyperpolarization, which means the cell becomes increasingly more negative. It moves from the resting potential of -60 toward -70 microvolts and lower. Depolarization is the process by which a cell decreases in polarization, meaning it moves from the resting potential toward -50 microvolts and higher. The greater the stimulus, the greater the response will be, so this change in neuronal potential is called a graded response. Graded or local potentials are stimulated at a specific site and travel passively across the cell membrane. These potentials diminish over time and distance. Once the membrane charge reaches threshold, the action potential is triggered under a rule of all or nothing, meaning once the potential reaches a certain point, typically -50 microvolts, the action potential will be triggered with complete energy.